session or in my session? Previous session? Okay. So I'll just revise, okay? So what we do is input some input parameter, input values, right? In this example, we are predicting if someone is overweight or not using their height, weight, and gender as input values. So what we do is take this input, forward propagate it, calculate the error, back propagate the loss, back propagate the gradient with respect to the loss, and update the parameters, right? So this can be done in multiple ways, right? Using whole data sample at once and calculate the gradient once. Calculating the gradient using whole data set. That is one way. Stochastic gradient descent, that takes only one sample and calculates the gradient. Why stochastic gradient descent? Because the number of input might be very high, and that way computing the gradient might be very expensive. So you take only one input and calculate the gradient. But that actually causes noisy gradient signals and might not converge fast, right? But it also helps to, because it's noisy, it doesn't get stuck in local minima. So if you look into current architectures, there are a lot of parameters. Like this is 60 million parameters, but you know how much parameters nowadays neural network has, like billions of parameters, right? How do they train them? How do they train them? It's exactly the same equation for linear logistic regression that they use to train billion parameter models. Like, but what you use to train two parameters, M and C, is the same algorithm that is used to train 2 billion parameters. That is the back propagation, right? So back propagation is just calculating of the gradient, like with respect to loss, with respect to error, and you find the gradient with respect to z at first. First you find the gradient with respect to z, and you compute the gradient with respect to y and x from the gradient of z. Like from dl upon dz, you compute again dl upon dx, but it is dependent upon dl upon dz, as you see here. Do you see it in the slides? Yeah. So first you calculate dl upon dz, and z is dependent upon x and y, right? Z is a function of x and y. So the gradient of x is also dependent upon the gradient of z. So gradient of z, dl upon dz, dl upon dx, that is the gradient of x, is dependent upon the gradient of z. And if you do chain of computations like this, you feed z into another function, and that output into another function, like we did in multiplier quotient. You need to get the gradient of input, like x here. Then you calculate the gradient with respect to input for all values. Like you get the gradient of the output, you calculate the gradient of the input from that. You do this in chain-wise fashion. That is called the back propagation algorithm. That's actually chain rule of calculus, if you know. What do? You give data samples and feed it to the model with parameters. You get a prediction, but that prediction is not always right. So you calculate the gradient. So gradient, I am throwing away gradient term, but if you guys don't understand what I mean by gradient, please let me know. You understand gradient? Yes. stochastic gradient descent, it means you calculate gradient using only one sample. In gradient descent, you use all the data points, calculate the gradient. In the gradient, there is a mean with respect to all the data points. Like one data point says change the b to change the parameter this way, another react says change the parameter that way, another react says change the parameter that way, and you calculate the average of all of them and calculate the gradient overall, right? But for stochastic gradient descent, some data will say change the direction that way, so you go that way, and another say no that way, you go that way, no another say that way. So that is very rough process. But if you use full batch, then you accumulate all the gradients and go to the average direction. And minimax gradient descent is between stochastic gradient descent and full batch gradient descent. You use small sample of data points to compute the average direction. In the figure, you can see full batch gradient descent, it goes to the minima very less noise, and stochastic gradient descent has the largest amount of noise. Like every data wants to have different parameters. And in mini-batch, it's in the middle way between stochastic gradient descent and batch gradient descent. In general, we always use mini-batch gradient descent. And in mini-batch gradient descent, you have to pass like batch, multiple batches of input data, and when you compute the entire data set, that's called one form. Yeah, I repeated this all the time, right? Forward pass, calculate the prediction, get the error, right? This is Jacobian. It's also a gradient with respect to the error. But still, there is problem in trading. What's the problem? When using multi-layered neural network, it isn't converged. Right? So there are multiple solutions. Like when you use multiple layer of neural network and try to fit the data, it didn't even converge. Even smaller network did well, but larger network did not do well. So stochastic gradient descent is about going to the slope of the pointed by the gradient, right? You go to the minimum, and I showed in the like ball-like figure, right? But there is a way to accelerate the momentum towards going towards the minima. That's called the momentum-based method. That's like acceleration in gravity, right? When you leave a ball from the hilltop, it goes faster and faster as it goes away, right? Starting is slow, but it accelerates. So adding acceleration to the gradient detection is what momentum does. If the direction goes always towards the same direction, it accelerates more and more. So stochastic gradient descent, it might have like very noisy solution, but using stochastic gradient descent with momentum, you'll get there faster because it accelerates towards the direction. I wouldn't get. Do you want me to go into the details of the equation? Yeah, we don't have time. So basically, yeah, okay. So this update term that we use in gradient descent, only the lower term, like only the term we use like something. We don't have it here. Sorry. Without the momentum, we only move towards the gradient direction, right? But here we add a momentum term, like that stores the information of how fast the gradient is changing. Okay, so basically, this is the gradient, this term delta L xt. This is the gradient, and we add the previous step, momentum of previous step with the current gradient. Momentum is how fast it is going, and gradient points towards, okay, still gradient and momentum face different angle. Like momentum says go this way, and loading this gradient says go that way. Like that, in this way, in this case, like if the momentum and gradient are opposite, then the momentum will decrease over, because it's like a force opposite, right? It's going that way, but gradient is pushing it that way, so it should slow down. But if it is going that way and gradient is also pushing it that way, then it will accelerate towards that. So it's like acceleration down gravity. Like is to make like momentum might go very high, like momentum might be very high and it might escape the minima. So it might reach the minima, but momentum is very high. So it will go up the hill. Okay. Basically, if you don't have minima, it will go towards the minima, right? But if it still has the momentum, then it will escape the minima and go away. So it has to be damped, like a frictional force. If you don't have a friction and you throw a ball from the hilltop, it will go to the minima and go up the hilltop, right? Maybe. Yes, it's a hyperthermic. Yes. Yeah, it's like balancing.
Huh?
Yes, yes. It's similar to that, but not exactly, because different scenario meaning different things. So momentum also, there was a problem because it escaped the local minima, right? So even after reaching the minima, it might go up. So look ahead minima becomes like before computing the object, if you look at the momentum and gradient. Right? First, you calculate change in x, and then calculate the momentum. Here we use momentum from gradient of current x, right? Like momentum, you observe the difference between this momentum and this, right? So here we use update the x first and then calculate the momentum. So this prevents it from escaping the local minima much. Right? Let's not go into the details of, because we don't have much time. So there are other factors of learning, like anagram. It tries to decrease the learning rate as you go on by summing the square of confidence, right? And these are all improvement upon the momentum. Like ARA data, it also improves using another term like gradient of the previous step, right? RMS drop also uses the momentum in different way, like second order momentum. And Adam, I'll say this is like a combination of multiple previous methods that uses momentum as well and second order momentum, as well. So it calculates momentum, and on top of momentum also it calculates another term, VT, like second order momentum, that helps it to accelerate faster and also stable when it reaches the minimum. Let's not get into this again. And with this, another problem, like use of sigmoid activation function that has a gradient, very low gradient, and when we use this, we get a less and less gradient as we move backward. Right? This is shown by this motivation speech you might have seen, right? If we do 1.01 onward work for 365 days, then right? So when you go layer by layer, the gradient decreases. It decreases to the point that it doesn't even optimize the parameters. It doesn't change the parameters. So what was the solution? One of the solutions was to use the identity correction, which let the gradient skip these weight layers and directly flow towards the input. That was one of the solutions. And another solution was to initialize the weight to be Gaussian distributed. And another solution to use batch normalization. If the inputs are spread all over, then it normalizes to have standard mean and one standard deviation, like 0 mean and 1 standard deviation, which also helps to have better gradients. So deep learning means these set of techniques, like that. These set of techniques that helps to train deeper models and generalize better. And these settings include optimizers, the use of momentum-based optimizers, RM, right? Learning rate, change in learning rate that might not find the local minima, or if we use small learning rate that might not reach the minima. Batch size, weight decay, dropout, like dropout, did you cover dropout? Okay. So overfitting is also another problem because we don't know how much the network, how much net capacity is needed. So that is treated by using dropout, weight decay, or data augmentation to increase the data points. Right. Dropout is actually, what dropout actually does is that it removes some neurons at training time. It helps to it helps neural network not to depend entirely on single neurons. Like if one neuron, this one neuron is used frequently and model is highly dependent on, then if the dropout removes it, other neurons have to learn its function. Like it's like distributed representation. Like in your brain as well, you might have some neurons dying and some neurons generating. So still you are you, right? It doesn't change the overall function of you. So this is similar principle. Like even if some neurons are removed, it still functions in roughly the same way. So I don't know. Sorry, it's not like that. So it's like distributing the functionality, not only depending on only one neuron. Like, if your university depends only on you and you leave the university, then your university collapses. But if it depends on multiple people and even if you leave, then your university still runs, right? So it's something like that. So this lambda here, this is actually weight decay, right? You actually want to reduce the magnitude of weights when you are training. Weights will be always increasing and it might be causing some problems. So you always decrease a small amount of magnitude of the weight. Like if it is 0. If it is 1.5, then you make it 1.44 or 45, right? In the next iteration. And it still does not affect the function much, but it helps to prevent overfitting. And about loss in deep learning, like you can use multiple loss, gain loss, L1 norm, L2 norm, cross entropy, binary cross entropy. I don't think I want to bore you in these details. For multi-class classification, like I want to talk on this because in the lab session today, you usually have the application to this. Basically, it's also similar to activation function, like softmax activation function. What it does is that it converts neuron again outputs neurons, and you apply shock max over it. And if the first neuron has high probability, then you will be sure that it is a 1.